Welcome to another video on the normal distribution. This is a great series of videos to help you truly understand the normal distribution. In this video, we're going to use the normal distribution for combined random variables. So before we dive too much into actually use the normal distribution, let's remind yourselves about combining random variables. All right, recall that combining random variables means one of two things. Either taking two or more random variables together, adding them or subtracting them, or repeating a single random variable multiple times. So taking two or more random variables together would be an example of like you have the mean and standard deviation for how long it takes to wash a car, the mean and standard deviation for how long it takes to wax a car, and you add them to figure out the total time to wash and wax a car, or maybe you subtract them to look at the difference between the time to wash and wax a car. Versus repeating a single random variable would be, okay, I know how long it takes to wash a car, but what about washing 5 cars? So I'm going to repeat that random variable of washing a car, washing a car, washing a car, washing a car. So those are two different situations where we're working on combining random variables. Now, there are a couple of rules we got to remember here. So if the random variables being combined follow a normal distribution, then the distribution of their combined values also follows a normal distribution. Okay, this is awesome. So if the variables that we are combining both follow a normal distribution, then when we combine them to look at their total by adding them, or look at the difference by subtracting them, or if we repeatedly do one random variable, that total will also follow a normal distribution. That's huge news for us, because that means when we're done combining random variables, we could utilize the normal function and we could utilize the inverse normal function as well. So a couple reminders when it comes to combining random variables. First, we got to talk about combining means, because if we're going to use that normal distribution, it all comes down to knowing your mean and your standard deviation. So combining means is pretty straightforward. All you have to do is add them, subtract them if you're looking at the difference, or you could even multiply them if you're doing it to speed up addition. So if you're repeating a random variable, washing a car, washing a car, washing a car, you are allowed to multiply to speed up that addition, but only because multiplication is repeated addition in this situation. So working with combining means is really, really simple. You kind of just do what you're supposed to do, right? But remember, there's a couple really good rules when it comes to combining standard deviations. First, you cannot under any circumstances add or subtract standard deviations. However, you can add variance. Now, don't let variance scare you. Variance is simply standard deviation squared. So if you have your standard deviation sigma and you just put a little square on it, boom, now all of a sudden you got variance. Once you have, there's a big typo right there. Once you have added all of your variance together, you would need to square root all of that variance to get back to your combined standard deviation. So a process you should be familiar with if you have already done that unit on random variables. Now, another key thing to remember is variance always adds. Even if a problem is asking for the difference between two variables, variance still adds up. If you got washing a car and waxing a car, and you look at the total of them, or you look at the difference between them, you're still looking at two random variables, so the variance always adds, no matter what. So keep those rules in mind, because I'm going to use those rules when we start to work on some of these probability questions. So, key thing, the mean and standard deviation is all you need. If you want to use that normal function, if you want to use that inverse normal function because you're working with a normal distribution, you need to be able to always think about what is my mean and what is my standard deviation for the question that is being posed to me, okay? All right, so we're going to look at 4 examples right now, and hopefully all 4 of them are a little bit different, so don't give up after the first one and think like I got it. Take your time and watch all 4 of these videos. All right, first one. Doug and Mary contribute money to charity each year. The amount both contribute varies according to a normal distribution. Doug has a mean of 250. So I'm going to do mean D for Doug. Doug's mean is 250, but sometimes Doug can give more, sometimes he can give less. So he has a standard deviation of $15. Then we have Mary. Mary's mean donation, this is for Mary, use an M for Mary, is $280. And sometimes she varies as well. Sometimes she gives more, sometimes she gives less. So the standard deviation for Mary is $30. What is the probability that their total donation to charities is more than $550? So the question is literally finding the probability that their total, I'll use a T for total donations, is greater than $550. Now, the most important part is that it says both of them follow a normal distribution, which means when I combine them here in a second, that will also follow a normal distribution. So to actually answer the question, the first thing I'm going to need to do is figure out a z-score for 550. Where does 550 fall in this total combined normal distribution? Well, to find a z-score, I need a mean and I need a standard deviation. So let's start there. What is the mean for the total? Well, this is so straightforward. I'm just going to take Doug's, typically around 250, plus Mary, typically around 280. I'm going to add those together, grab a calculator if you can't do that pretty simple math in your head, and that's $530. So I'm already thinking that to have a total greater than 550 is going to be on the lower side. It's definitely going to be under 50%, but it should still happen because, again, both of them do deviate. So what about the standard deviation for my total? This is where I got to remember I cannot do 15 plus 30, 45. The number one rule is you're not allowed to add standard deviations. But I am allowed to add variance. So Doug's variance is simply 15 squared. Don't even worry about what 15 squared is. Just putting that little square on the 15 makes it variance. Mary's variance is 30 squared. I'm going to add up all that variance. Then I'm going to square root all of that variance to get back to a standard deviation. Please do not have such bad algebra skills that you'll think those squares are going to cancel. That is simply not true when there's a plus sign there. So I'm going to go right to my calculator. I'm going to start that giant square root. 15 squared plus 30 squared, all inside the square root. And there it is, $33.541. So if I simply go up one standard deviation, I will be at about $563. So it definitely seems like it's probably going to be likely that they could donate more than $550. So the last piece of this puzzle here is I need that z-score, because now that I know the mean and the standard deviation for the total, I could find the z-score for a total of 550. But I couldn't do that until I had the mean and standard deviation. So the mean for the total is 530. The standard deviation for the total is 33.541. So now I'm going to go to my calculator to get that z-score. 550, whoop, too many fives there. 550 minus 530. Again, where did I get the 550 from? That was the number that the question asked me about. Divided by the 33.541. 1, not 0. And I get a z-score of 0.596. So, if you think about, you could even draw the normal model if you want. 530 is going to be in the center. And if I go up one standard deviation to the right, that's going to be around 66. So 550 makes sense to be under one standard deviation. So now I'm going to come back, right? This is where I'm going to need my calculator, because my calculator does not understand total amount of money donated to charity, but it does understand z-scores. So asking about the total being greater than 550 is the same as a z-score being greater than 0.596. And that's where I could use the normal function on my calculator. Second vars gets to my distribution list. Normal CDF is the normal function. We want to go 0.596 as my lower to a greater value of infinity, which I'll use 99. So 0.596 is my lower, and I'm going higher, higher, higher than that, which would be technically towards infinity. So I'm just going to use a 99 there. And I get 0.276. 0.276. So there is the answer to the question that was asked. The probability that the total is greater than 550, that's a z-score greater than 0.596, and it's got about a 27.6% chance of occurring, which is really, really likely, actually, that they could contribute more than $550. All right, next question. Kevin and Bobby are both pretty serious bowlers. Their scores both follow normal distribution. Kevin has a mean of 240, so Kevin's mean is 240. He's bowled lots of games. He has an average of 240, but he's got his good days and his bad days, so Kevin's standard deviation is 10. Then we got Bobby, who's a little bit better on average than Kevin. He has an average of 255 pins. Standard deviation for Bobby, and he's got his good days and bad days as well, is 18 pins. All right, the question now wants us to find the probability that in a random game, Kevin has a higher score than Bobby. Okay, this is actually one that we have to really think about. This is a really typical AP question because it involves a lot of good thought process here. So what is the probability that a random game Kevin scores more than Bobby? Okay, so let's think about this for a second. If you're comparing two people, I'm comparing Bobby to Kevin, you're looking at their difference. You're looking at their difference. So I need to think about what is the expected difference. I'm going to use a D for difference there. So if I typically think about the fact that Bobby minus Kevin, that's Bobby 255 minus Kevin 240, that's a 15-pin difference in favor of Bobby, right? In favor of Bobby. So I'm looking at that difference. Now, what about the standard deviation? Because again, you know what? they're going to vary. Kevin's going to vary. Bobby's going to vary. So there's definitely a standard deviation here as well. So I'm going to take the variance, because I'm not allowed to add or subtract standard deviations. So Kevin's variance is 10 squared. Bobby's is 18 squared. But remember that rule, variance always adds, even in a problem where you're looking at the difference. So I still am going to add those. So I'm going to go and get my square root here. 10 squared plus 18 squared, all inside the square root, 20.591. Okay, now, what's the question asking? Once again, the question is asking that Kevin scores more than Bobby. So let's think about this for a second. If the difference is 0, that means that they're tied. They're completely tied, okay? Anything greater than 0 is a positive number. And I did the difference in a specific order of Bobby minus Kevin. And if I'm thinking about that order, Bobby minus Kevin, if Bobby is bigger, I'm going to get a positive number. So think positive values mean Bobby wins. Bobby does better. Because again, if I'm thinking about Bobby minus Kevin, if Bobby has a higher score, when I do Bobby minus Kevin, I'm going to get a positive number. A negative result, though, would be what Kevin does better. Because again, think about that. If the K is bigger than the B, if Kevin does better than Bobby, when I do the subtraction of Bobby minus Kevin, I'm going to get a negative number if the K is bigger. So if they're equal, I have a 0. Anything less than 0, which is the definition of a negative number, is where Kevin does better. So I'm actually trying to find the probability that the difference is less than 0. Because when the difference is less than 0, in the order that I did this, Bobby minus Kevin, when that difference is less than 0, that has to mean that the K was bigger. And if the K is bigger, Kevin does better. Boy, that's tough to figure out. That's tough to process. So please really take your time on that. All right, so what I need to do is find the z-score for 0. The difference is supposed to be 15, and I know it could go more and it could go less because of our standard deviation. So I need to find the z-score because, again, my calculator does not understand a difference of 0 pins. My calculator does understand 0 as or the z-score for 0. So I got to find the z-score. So 0 is the number I'm looking for. Hope everybody really understands why. Minus, it's supposed to be 15. Like, listen, Bobby's supposed to do better. Divided by the standard deviation of 20.591. So grab your calculator, 0 minus 20 on top. And I'm going to go and divide that by the 20.591. And we get a z-score of negative 0.971. Negative 0.971. So if I find a z-score less than negative 0.971, that's equivalent to a difference less than 0. And I hope you understand that a difference less than 0 means Kevin will do better. Now, listen, what's supposed to happen is Bobby. Bobby should always do better, right? Not always, excuse me, but Bobby should be more likely for Bobby to do better because first off, 15 is what Bobby should do better than Kevin. But even if you just think about a difference of 0, anything on the greater side of that, the positive side of that, is where Bobby will do better. I'm looking at the negative side of 0. So I'm going to go ahead and grab my normal CDF. It's my normal function. This time I want to go below my z-scores. I'm actually going to start at negative 99 as my lower value, negative 0.971 as my upper value. And essentially I'm looking below a z-score of negative 0.971, which is a difference below 0. And I get 0.166. So there is a 16.6% probability that in a random game, Kevin will do better. Kevin just has to vary on the high end, which he could do because he does have a standard deviation. Bobby has to vary on the low end, which he could do because he has a larger standard deviation, and that would allow Kevin to do better. That's a really good AP question. Please really take your time on understanding that one. Okay, example 3. A summer resort rents rowboats to customers but does not allow more than 4 people in a boat. Each boat is designed to hold no more than 800 pounds. Suppose the distribution of adult males who rent boats, including their clothes and gear, is a mean of 190. So the mean for an adult male is 190 and the standard deviation is 10. But remember, there could be no more than 800 pounds amongst the 4 people. So the question is, what is the probability that the 4 male passengers will go over, that's the total going over 800 pounds. All right, good news is that a single male follows a normal distribution, which means if I put 4 of them together, that total will also follow normal distribution. But the problem is I need to first figure out what is the mean for the total of 4 men and the standard deviation for the total of 4 men. Then what I could do is find the z-score for 800 and use my normal function to look above that z-score, because my normal function on my calculator does not understand 800 pounds. So, all right, I know what a single man looks like. What about the total for 4 men? Total for 4 men. Well, that would be 190 times 4. 190, 190, 190, 190. 190 times 4. Now notice here I'm using multiplications to simply speed up addition. 190 times 4 is 760 pounds. So 760 pounds is less than 800, so this is why we would expect to not go over the acceptable weight limit, but you never know because it could vary. So what about the standard deviation for the total? I'm not allowed to combine or add standard deviations. So I'm going to take 10 squared, that's the variance for 1 male, and I'm going to times that by 4. Or again, you could do 10 squared plus 10 squared plus 10 squared plus 10 squared, because you have 10 squared 4 times for the 4 men, but you can't multiply 10 times 4 because that would be repeatedly adding standard deviation, and you're not allowed to add standard deviation. I'm going to need a giant square root around all of this to get that variance back to a standard deviation. So 10 squared times 4. And again, really, that's the tricky part here, is making sure you understand that. And I get a standard deviation of 20. Now I can find that z-score that represents 800. So 800 minus the mean of 760 divided by the standard deviation of 20. Grab a calculator if you need to. Just take your time, and that is a z-score of exactly 2. It kind of works out when it's a nice value. So asking about the probability exceeding 800 is the same thing as a z-score exceeding 2. Now I could go to my normal CDF on my calculator, and I could find the probability that the lower value is 2 and the upper value is 99, because I want to go way above 2 to the right. That's greater than, and I get 0.0228. 0.0228. So that's certainly not very likely, but it's still possible. So I would say they should be somewhat concerned that this could happen, but it's still on the lower side. I want to quite say it's unlikely because it's not underneath 1% quite, but it's pretty low. So overall, it's not going to happen very often. All right, key thing there is making sure you know how to combine to get your total mean and your total standard deviation, and then using normal CDF. All right, one more problem and we're out of here. A 100-meter relay race contains 4 swimmers. Each person has a time that is approximately normal. That's huge. That means if I combine them, the total will also be normal. Now, to qualify for a tournament, they must swim the race under 465 seconds. So here are the individual times for Mike, Dave, Greg, and Lucas, means and standard deviations. And to qualify for a big tournament, they need to swim a race under 465 seconds. What is the probability of that happening? So what is the probability that their total is less than 465 seconds? All right, to do that, I'm going to need a z-score that represents 465 seconds in a normal distribution for the total. So I first need the mean for the total. Well, that's easy. I'm just going to take, let's see here, I'm going to take Mike's score of 115. I'm going to add Dave of 121. I'm going to add Greg of 118. And I'm going to add Lucas of 120. And I get a total of 474 seconds. So that's what they should expect to take. So they're going to have to all put on their best scores here to hopefully get lower, because they need to get under 465. But what about the standard deviation for their total? Well, please, I'm begging you, you cannot add standard deviations. What you can do is take Mike's variance, 2.3 squared. Whoop, that did not work out well. 2.3 squared, plus Dave's variance of 2.1 squared, plus Greg's variance of 1.4 squared, plus Lucas's variance of 4.2 squared. And then I need a giant square root around all of that to get back to a total standard deviation, 5.413. And both of those are, of course, in seconds. All right, now I could get the z-score for their total, because, again, I'm trying to find the probability that they get under 465 seconds. So this might be kind of hard, but let's see what happens here because they're only supposed to get a total of 474. But if all of them deviate on the low end, it is possible. So I'm going to find the z-score for 465 because that's what my calculator is going to understand. So 465 minus the 474. Don't forget to hit enter first. They need to do 9 seconds below what's typical. Divide by 5.413. And I get a z-score of negative 0.1663. And that's the z-score I'm looking underneath. So my calculator doesn't understand 465 seconds, but it certainly does understand z-scores. So now I'm going to go and grab that normal CDF command here, and I want to look below. So I'm going to start at negative 99, and I'm going to go up to that negative 1.66. Whoop, it's hard typing on this thing. 663, and I forgot a decimal. Come on. Boy, I'm all over the place today. All right, so there I go. So I'm looking below that z-score, which is essentially looking below a total time of 465. And what do I get here? I get, 0.0482, 0.0482. So there is a chance. Now, again, they're both going to have to do really, really good, but there is a chance, about a 4.82% probability. So if Mike, Dave, Greg, Lucas all dig down deep and go as fast as they can, there is a, I don't want to say completely unlikely. It is lower, but I wouldn't say it's impossible to do. They could definitely do it. They're just going to have to really swim their best. All right, that's it. Hopefully you learned a lot in this video. Hopefully it was a good review of combining random variables, but it's also this idea of when you do combine random variables, if they follow a normal distribution, so does their combined values. All right, hopefully you enjoyed it. See you later.